Hello everyone, this is Mr. Underkoffler. Today we're looking at the guided notes called Zero Power and Powers of Monomials. All right, let's start with the power of zero. Anything except zero taken to the power of zero is equal to 1. Now this might surprise you. So it doesn't matter what this number is, as long as it's not zero. Any number other than zero taken to the zero power will equal 1. Now, in case you're wondering, 0 to the 0 power is undefined, which means there's no mathematical definition for how you can even do it. Now, you might be like, what in the world is all this nonsense about? Okay, let me show you how this actually makes sense. I picked two random bases here, powers of 7, powers of 16. 7 to the third is 343, 7 to the second is 49, 7 to the first is 7. Here's what I want you to notice. If you go top down, you could continue dividing by 7 to get to the next number going down here on exponents. So if I continue going down by one of the exponents, then I would have to divide by 7 again. Well, what's 7 divided by 7? Pencils in your hand. Boom, write it down. It's 1. You're like, well, does that always work? Well, here's another one. 16 to the third, 4,096. 16 to the second, 256. 16 to the first, 16. Notice we could continue dividing by 16 to go from one answer down to the next as these exponents continue to go down by 1. So, following the pattern, making 16 to the first now go down to 16 to the 0. That means I would have to divide by 16 again. And what's 16 divided by 16? 1. Now, why is 0 to the 0 undefined? Why can't you take 0 to the 0 power? Well, here's the problem. Then if you would apply this pattern with the base being 0, you would be required to divide by 0, which you can't do. We talked about this, I think, earlier this year. Dividing by 0, you can't do it. There's no mathematical definition for it. So that's the problem with taking 0 to the 0 power. It's the only number that you cannot take to the 0 power. Any other number other than 0, if you take it to the 0 power, it will give you 1. Even if the base is negative, take it to the 0 power, it's still going to equal 1. And you could prove it by doing this type of pattern yourself. Okay, so with that in mind, over on the right-hand side of your paper, hit pause in the video, do number 1, do number 2. Number 2 requires you to remember the rules of what do you do with exponents when you multiply like bases together. If you forget what that rule is, feel free to pull out the previous guided notes on multiplying and dividing monomials. All right, so I'm going to ask you to hit pause on the video, do number 1 and 2 on your own, and then hit play once you're ready to see how you did. Okay, did you already do number 1 and number 2? 529 to the 0 power. Wow, 529 is big, but it's taken to the 0 power. Answer is 1. Problem number 2. I would not find out what 4 to the 5th power is, and I would not make 4 to the negative 5 become 1 over 4 to the 5th. No, 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 no. The easy way to do this is to add the exponents together. And 5 plus negative 5, boom, is 0. 2 plus negative 2, boom, is 0. Now we got 4 to the 0 times 11 to the 0. Don't multiply first. Do the exponents. 4 to the 0 is 1. 11 to the 0 is 1. And 1 times 1 is 1. We're not going to do a ton of examples on this, but hopefully you're getting the point here. Any number other than 0 taken to the 0 power is equal to 1. Okay, let's move on. Let's talk about the main rule of these guided notes, and that is what do you do with powers of monomials? You're like, what does that even mean? Well, if I have a monomial like x to the second, and I take that to the third power, so the entire thing inside of the parentheses is taken to the third power, well, how would I do that? Well, anything to the third power means times itself, and times itself, again, a total of 3 of those factors. So you would have x to the second times x to the second times x to the second. Well, what did we just learn about when you multiply like bases on the previous guided notes called multiplying and dividing monomials? We learned you can add their exponents together. So 2 plus 2 plus 2 would give you, boom, x to the 6th power. Well, what if there was more stuff inside of the parentheses taken to a power? Well, then that would be that 5y to the 6th times itself again, times itself again. Now, if I use the commutative property of multiplication, I can rearrange this and put the 5's all with each other. That would be the same as 5 to the 4th. Put these y's with each other. You could do the trick that we were talking about over here. Add their exponents. 6 plus 6 plus 6 plus 6 would give you 24. And then 5 to the 4th, well, 5 times 5 would be 25. Times another 5 is 125. Times another 5 would be 625. So that's how I got this answer. You might be sitting there and saying to yourself, wait a minute, Mr. Underkoffler. I'm noticing a shortcut here. Instead of doing the work that you showed, couldn't I just do something with these exponents? Do you see what I'm talking about? I bet you do. Get your pencils ready. We're going to fill in the blank here. Here are the shortcuts to find the power of a power. You can multiply the exponents. You probably saw it back here on x to the second taken to the third. If you take 2 times 3, boom, you would get 6. Even over here, 5y to the 6th. If you would take 6 times 4, boom, you would get 24. So when you have a base to a power and that's taken to a power, you can simply multiply the exponents together. Now, what if we have more than one thing in the parentheses, some kind of product, some kind of multiplication problem? That's what product means, multiplication problem. And that's, in parentheses, taken to a power. Well, you can basically just take both of those factors and put that power from the outside of the parentheses to both of those factors. So let's fill in the blank. We're going to find the power of each factor and then keep multiplication in between. You don't have to put a times dot in between because it's still meant to be times if it's a variable next to another variable, even though they're both now taken to a power. So let's, and I hope you guys, forgive me if I'm jumping ahead here. I hope you saw that over here with the 5y to the 6th. You could just take the 5 to the 4th and the y to the 6th to the 4th, which requires you to multiply the exponents. So that's the trick here. Let's practice both of these rules. So we have 2 to the 2nd taken to the 4th. What did we learn? When you have something to a power, and that's in parentheses taken to another power, then you can multiply the exponents. So, boom, let's write this down. We can take the exponent of 2, the exponent of 4, multiply them together. Please show the step of work for now. Eventually, you might not have to show the step of work, but for now, please write it down. And 2 times 4 is what? Boom, that's 8. The directions say simplify, so this is not as simple as it actually could be. Let's figure this out together. 2 times 2, I'm actually using my fingers right now to keep track, so I know. 2 times 2 is 4, so that was 2 to the 2nd, times another 2 is 8, so that was 2 to the 3rd, times another 2 is 16, times another 2 is 32, times another 2 is 64, times another 2 is 128, that was 2 to the 7th, so times another 2, 128 times 2, you can do it off to the side if you need to, but it is going to be 256. Yeah, it was nice that I did that one with you. You're welcome. All right, let's do number 4 together. Oh, we have a product inside. What do we just learn? Each part of the product, each factor of the product will get taken to the power. So the -3 will get taken to the power of 4. Yes, the -3 needs to be in parentheses. We've talked about this over and over again in this unit. When you take a negative number to a power, you must put the negative number in parentheses and the power on the outside. Now, we also are going to go ahead and take the 4th power to the end of the 7th, which, how do we do that? We multiply the exponents together. So I hope you're writing this down. Now, let's figure this out together. -3 times -3 would be +9, times another -3 would be -27, times another -3 would be +81. Now, you probably remember that if it's an even exponent, that you'll get a positive answer. You probably remember that. All right, how about n to the 7 times 4? Well, that would be n to the 28th. All right, let's just do one more together just to make sure we got these two rules here secure. We got a product of 3 different things here. We got a coefficient, 2 different variables, and this one's to take it to a power. By the way, just so you are aware, I think I mentioned this on other guided notes, but only the c here is taken to the 7th. If I wanted both A and C taken to the 7th, then I would need another set of parentheses to show that. Or I would just simply say A to the 7th and C to the 7th. So you need to realize, according to order of operations, only the C is taken to the 7th, not the A. Okay, now that we got that cleared away, let's go ahead and use the shortcuts that we talked about. So the 18 will be taken to the 2nd, the A will be taken to the 2nd, and the C to the 7th will be taken to the 2nd power, which that's where you do the other rule we talked about, multiplying their exponents together. Okay, what is 18 to the 2nd power? Well, you could go off to the side and figure it out, but spoiler alert for later in this unit, you're going to have to memorize your what we call perfect squares, things to second powers, up to 20 to the 2nd power. So you will eventually have this memorized. I promise you, you eventually will. You probably don't yet, but you eventually will. All right, A to the 2nd is not going to change, but C to the 7 times 2, that would be C to the 14th power. Okay, so now that we have done 3 problems together, time for you to try some on your own. 6, 7, and then if you go down to the next row, you'll find 8, 9, 10, and 11. I kind of ran out of room for the work for 11, so I kind of dropped it a little bit lower. But yours is just in line with the others. So I want you to do these 6 remaining problems, 6, 7, 8, 9, 10, and 11. So hit pause in the video, do those 6 problems on your own, and once you are done with all 6 of them, then hit play so you can see how you did. Okay, have you already done 6, 7, 8, 9, 10, and 11? If not, you better hit pause now because I'm going to go over them. All right, hopefully on this one, you took the exponent of 2 times the exponent of 3, giving you 3 to the 6th, and then hopefully you figured that out. That is 729. Over here, we multiply the exponents and we get W to the 55th, and that's it. There's no other work to that problem. Problem number 8, both factors had to be taken to the 4th power, so we're going to use both shortcuts here. Both of them are going to get the 4th power multiplied to the exponent that we used to have. 3 times 4 will give you 12, 2 times 4 will give you 8, and there you go. If you need to hit pause on the video to fix your work, please feel free to do so. Otherwise, I'm going to continue moving on here. Problem number 9. The negative 8 gets taken to the 2nd power. Did you put that in parentheses? Please check. If you didn't, fix it. It does matter. It does matter. All right, m to the 5th times 2. And negative 8 to the 2nd would be negative 8 times negative 8, which is a positive 64. And then 5 times 2 is 10. 64m to the 10th. Problem number 10. The 5 is going to get taken to the 3rd power. The C is going to get taken to the 3rd power. No, that C was never taken to the 9th. Only the D was taken to the 9th. Just like I mentioned back when we were talking about problem number 5. Only the C was taken to the 7th on that problem. So back to where I was. D to the 9th taken to the 3rd would be 9 times 3. 5 to the 3rd, well, 5 times 5 is 25. Times another 5 is 125. We got C to the 3rd, and then 9 times 3 is 27. So D to the 27th. And finally, problem number 11, the negative 2 in parentheses, taken to the 5th power. Yes, you better have those parentheses. If you don't, fix it now. X to the 7th times 5. Y to the 13th times 5. Negative 2 to the 5th. All right, 2 times 2 is 4, times 2 is 8, times 2 is 16. That's only 4 2s so far. Times another 2 is 32, but it's going to be negative. You might remember earlier this year I taught you that if you have a negative base to an odd exponent, you will get a negative result. No, you're not going to make this become a fraction. This is not a negative exponent. Please do not think that a negative integer is the same thing as a negative exponent. Not the same thing. So no fraction here. Okay, let's continue. X to the 35th, and then y to the 65th. All right, let's go ahead and move on to the next page. If you needed to rewind the video and fix your work and hit pause, please feel free to do so. Otherwise, continuing on. Problem number 12. A square floor has a side length of this lovely thing, units, 8x to the third, y to the second. A square tile has a side length of x times y, units. How many tiles will it take to cover the floor? Now, you might be like, what in the world do I do with this problem? Well, this is why I'm leading this one. I'm going to lead you through this one together. So here's what I need you to think. And I have this typed up for you on your page. Get your pencil ready. We're going to fill in these blanks. Since we're trying to find how many tiles can cover the entire floor, I want you to think to yourself, is that perimeter? Is that area? Is that volume? Well, a floor is flat, so it's not volume. The tiles that fill up that floor would not be perimeter. It would be area. Fill that in. And the area formula, sorry, I had to have you put the word again. Otherwise, if I already had it here, it would have kind of given it away. But the area formula of a square, if you don't remember, you can look it up on your formula sheet. Hopefully you still have your formula sheet. But it's that the area of a square equals the side times itself, which is just the side to the second power, because the sides of a square are equal. They're congruent. So instead of length times width, it's just side times side, which is side of the second power. Well, here's why we're doing this problem in this page of guided notes, because this is about taking things to powers. So we have a side length. Yes, our S here, our side length is 8x to the third, y to the second. That's the side length of the entire square floor. So humor me here. Somewhere off to the side in your paper, draw a slightly big square and label it with its side length according to what the problem told you. But then a square tile, just one little tile that's going to make up this floor, well, a whole bunch of them are going to make up this floor. One little tile has a side length of what? X, Y. So, humor me. Somewhere near the big square that you drew, draw a very small square and label its side length as XY. And what we're going to do is we're going to use area formula of a square, except I'm not going to make you put a capital A and an equal sign, but it's basically going to kind of be like formula substitute solve, except we're only going to really focus on here the S to the second power, the side measure to the second power. So what's the first side measure we got? For the entire floor, the side measure is 8x to the third, y to the second, and we are going to take that to the second power. So write this down with me. And then what else do we have to do? We need to find the area of the little tile. So that's the side length of xy taken to the second power. Eventually, what we're going to do to find out how many of these little tiles is it going to take to fill the entire floor, we're going to end up dividing the area of the little tile into the area of the entire floor. So let's use what we learned. We're going to take 8 to the second, x to the 3 times 2, and y to the 2 times 2. I hope you're writing all of this down. If I'm going too fast for you, feel free to hit pause whenever you need to. 8 to the second is 64. 3 times 2 is 6. 2 times 2 is 4. So this represents the area of the entire square floor. Now let's do the area of the tiny, and you know what, this tile probably isn't tiny enough, but the way I drew it, but the area of that tiny tile, well, that'd be x to the second and y to the second. And now what we're going to do is we're going to divide them. I would recommend that you would show your division problem as a fraction, so that way you should trigger your memory on, oh, there's a shortcut for when you divide like bases. Now, you're like, what do I do with the 64? Well, the denominator, we don't even see a coefficient at all. So whenever you don't see a coefficient, that's the same as having a coefficient of 1. 64 divided by 1 is 64. So that's not going to change. But what about the x to the 6th and x to the 2nd? Do you remember the shortcut for that? You would subtract their exponents. So 6 minus 2, boom, 4. And then for the y's, subtract the exponents. 4 minus 2, boom, is 2. And what this answer does, this represents, in a very abstract way, because we don't even know what x or y equals, but in a very abstract way, this is the number of tiny little xy side length tiles that could fit in a floor that has side lengths of x or 8x to the third, y to the second. I know that's really abstract, but that's what this answer means. And now that we have talked about that, I would like for you to try number 13 on your own. I do have a little bit of a hint statement for you here. Notice this is no longer talking about a flat floor. We're talking about cubes. Hint, 3-dimensional. All right, so hit pause in the video, try 13 on your own, and then hit play once you're done and ready to see how you did. Okay, have you already done number 13? Hopefully you figured out this was volume. And volume is taking a side length of a cube to the third power. So did you take the 6x to the 10th to the third power and the side length of x to the fourth to the third power? If you didn't, hit pause now, go back and fix your work, and then hit play once you're ready to go from there to see how you did with your fixed work. Okay, from here, 6 to the third, 10 times 3 for the exponents. That's going to give you 216 for 6 to the third, because 6 times 6 is 36, times 6 is 216, and 10 times 3 is 30. Over here, we're going to get 4 times 3, which is 12, so we got x to the 12. And then like we just did on the previous problem, except that one was squares, this one is cubes, we're still going to divide to find out how many cubes, the tiny little cubes, will make the big cube. So 216 divided by 1 is 216. For the x to the 30th and x to the 12th, we're going to subtract their exponents, giving us x to the 18th. And there is your answer. Again, very abstract answer, but that's the number of cubes that it'll take to fit into the larger cube. All right, thanks for watching this video. We'll see you next time.